So, welcome again with this new lecture, an interesting one, where we are going to discuss some very simple laws stated by Kirchhoff. They are called Kirchhoff's laws, and there are two laws. One is Kirchhoff's current law, the Kirchhoff's voltage law, which in a nutshell is describing the conservation of charge and conservation of energy principles respectively. Okay. They're very simple. Well, we have an idea of both the laws. Of course, when we are talking about the laws, the key formula is V is equal to Ri, wherever there is resistance. And wherever there is a cell, for example, I have shown this cell, this is the positive and this is the negative. Okay. E and R, which is the internal resistance, which is also known as output impedance. But I'll talk about output impedance when we are learning AC circuits. So in these circuits that we are going to talk about, we'll call that DC, not AC, but direct current circuits. So if we are moving from P to N, okay, then you can see that from here to here there is no resistance, there is no voltage drop from here to here, but from here to here, this is the cell with an EMF, an ideal cell, in series with an internal resistance. So when we are traveling from here to here, then we encounter this small r, but the current in the small r is coming in this direction. Therefore, what we will write, Vpn will be equal to E minus Ri. Friends, this is the natural flow of current in the cell. I have shown another one, AB, where again the current is shown to come from B to A, going through this from the positive terminal to negative terminal, which is not natural, which is forced. Okay. But we are again traveling from left hand side to right hand side. Okay. So from right hand side to left hand side. So VBA, this we'll write as small r into I plus E. Okay. So this is how we are going to represent in the natural position and in the forced position of current, wherever that comes. Okay. So these are the key things which are involved in understanding of these laws. The first law is called Kirchhoff's current law, also known as the Junction rule. Okay. Here I have a junction. Okay. And in this junction, I have shown that there are branches from which a current I1 arrives into the junction, I2 goes out of the junction, I3 also arrives into the junction, I4 into the junction, and I5, like I2, is out of the junction. Now, the sum of the incoming currents is equal to the sum of the outgoing currents. Which current we'll consider as positive and which current we'll consider as negative? No problem. Whatever you feel good about. But if you brand one as positive and the other as negative, you have to brand the other as a negative. Okay. So, looking at this, I1 plus I3 plus I4 is equal to I2 plus I5. Okay. And if we look at a given time t, so for I1 there is a charge Q1 which is going into the junction. For I3 there is a charge Q3 which is going into the junction, and for I4 there is a charge Q4 which is going into the junction. Okay. For the outgoing, Q2 upon T plus Q5 upon T. All these T's will cancel out, and therefore we will get the sum of the incoming charges Q1 plus Q3 plus Q4 is equal to Q2 plus Q5. And this is one of the basic fundamental rules that charge cannot be created and charge cannot be destroyed. Okay. There is no transformation of charge also like transformation of mass into energy and energy into mass. That could be possible. But the charges are always conserved. So, what I say and what we say in Arabic, ma khalaq, ma fana. No creation, no destruction. And this is what we can write, that there is no accumulation of charges at junction, etc. I've shown this is the connector or whatever, and I have just taken a point here. This is not a junction, but this is like a Tundla junction where the trains are coming and trains are going out. But this is like any station where there is a single line, trains are coming and trains are going out of that. So in this case also we say that the incoming current is equal to outgoing current at this station. Okay, this is very simple. So this is basically a rule of conservation of charge. Now let us take KVL. This is called Kirchhoff's voltage law and also the loop law. I'm just taking a loop. I'm not putting any resistances, cells, etc. Just like that. Point 1, 2, 3, 4, 5. And in between there are some gadgets like resistors and like cells. Okay. So now let us travel from the point point 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 1. Okay. Now this is called coming back, homecoming. Okay. This we will call homecoming. Okay. So I can now see as to what is the sum of the potential drops or sum of the potential rises V12, V23, V34, V45, V51, and this will turn out to be equal to 0. So the net, okay, that means लौट के बुद्धू घर को आए. And this is what I also told you while we were discussing the gravitational potential energy rule. And this is something like this. I have this here. right now. I take it here, I take it here, and then I take it here, then I take it here, 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 and finally back to the same position. The sum of all these energies will be, the sum of all these energies will be equal to 0. So similarly, if I multiply it by a charge, a small q, okay, a small q, a small q, a small q, a small q, then this is the energy associated with this travel, energy associated with this travel plus this plus this plus this, and that is equal to 0. So what is this? This is the law of conservation of energy. The law of conservation of energy is what I've just shown, that this is the current I which is traveling around the loop, okay, continually without any loss of the current, etc. I'll explain these laws with the help of some examples. So let us take as an application of Kirchhoff's laws a very famous textbook problem where there are 12 resistances, each of value capital R, which we take as 1 ohm each, and they are on the edges of a cube. Okay, the edges of the cube. I did that A, B, C, D, A naught, B naught, C naught, D naught. This is how it happens. Now, this is an example of the application of the Kirchhoff's law, but it is more so an example of symmetry. You can see that this network, which is very complicated network in appearance, this is the beauty of symmetry. You can see at A we have 1, 2, 3 branches, and at C naught also there are 1, 2 and 3 branches, and I've just missed that this branch will also have a current which is equal to 2I. Well, I've been doing it. People have been doing it. Sometimes we take this current to be I, and then I by 3, I by 3, I by 3, I by 6, I by 6, I'm sorry, I by 6, I by 6, like that, okay. But what I'm going to take from experience, I take the current to be, you can see, between A and C naught, okay, there is a battery that has been connected, that is 10 volts and 0 ohms, negligible internal resistance. Okay. So with that, I see that this 6I is split in 3 parts equally, 2I, 2I, 2I. Let's see what happens to this 2I. This again is split into 2 parts, I and I, and this current coming from here and this current coming from here, they make it 2I. And similarly I get 2I here, 1 here and 1 here, and that makes 2I, and 1 here and 1 here, that makes 2I. So it's a complete case of symmetry. And in this case of symmetry, when once the currents have been distributed and we understand the currents are as it is, okay, then to solve the problem for determining the value of R equivalent between the points A and C naught. Okay, between this point and this point, now it is just a network of resistances, nothing else, but we can connect this like this, okay, and connect it like this, no problem. So let us take a closed loop. Okay, let us take a closed loop, including this branch which carries the cell. For example, I can choose, start from A naught, B naught, C naught, back to A. Again, let's start from A, D naught, C naught, like this. R, I start from this A, B naught, C naught, like this. Okay. So any of these loops we can take. Of course, there are many so many other loops which will not help us. For example, if you say this is a closed loop, okay, A naught, D naught, C naught, B naught, A naught. That will not help because the currents cannot be calculated without a source. So look here, I take, for example, A to A naught to D naught to C naught to back to A. Okay. So I have now I am going to write it for fall of potential. You can write it for rise of potential. There is no problem. So fall of the potential I can write here. I am starting from here, R into 2I plus R into I plus R into 2I, okay, and plus minus 10 volts, okay, is equal to 0. Because, like I said, laut ke buddhu ghar ko aaye. So we are back to the pavilion, okay. So this, when I work it out, and the value of R is taken as 1 ohm, so this becomes equal to 2I plus 2I minus 10. So that means 5I is equal to 10 and I turns out to be equal to 2 amperes. Okay. Then this current through each edge. You can see 2 into 2, 4 and 2 and 4, etc., etc. Okay, we can calculate the currents through okay. Some people like it current across each edge. No. It's voltage across each edge that we can talk about, but the current is always through a resistance. So we must talk about through each edge. Okay. That mistake is committed because we are Indians and we sometimes are poor in English. Okay, I too am. So then I can say that this between A and C naught, the total resistance is equal to R equivalent. I have not drawn there because it will become which pitch. Okay, so 6I and then R equivalent multiplied by R equivalent minus 10 will be equal to 0. Okay. Which means R equivalent into 6I is equal to 10. So I can write R equivalent is equal to 10 upon 6 into 2. Okay, I is equal to 2 amperes. So this is the volts and this is amperes, so 5 upon 6 volts. Okay. In fact, if each of them is R, then this result will be 5 upon 6 into R. Okay, so R can be taken as 2, then it becomes 5 by 3, R can be taken as 6, then this will be 5 ohms each. It can be taken as 6K also, so that way you can calculate the value of I, and on each edge, whatever you like. And also, if we are a little more cruel to you, we can ask, what is the power consumed by this? Simply I square R. Okay, so we can make those calculations. How much is the total power dissipated? Various values of I square multiplied by R, and because that will not be any algebraic sum, but it will be a simple arithmetic sum, we can calculate it out. But friends, be careful. Be careful in the sense that that symmetry which we are being very happy about, if we take this point A and this point B, which is also sometimes a favorite for teachers, okay, and asking you to do it, then you have to find other ways to calculate the value of R equivalent between the points A and B, and between these points you can put any value of cell, etc. Okay, and like this R has been taken as equal to 0, this can also be given some value, and you will be asked to calculate that. Then you calculate according to what I said, E minus IR, Ri, and E plus Ri, depending upon whether the current flow is natural or the current is pumped through it. Remember, I will just part with that. Okay, remember always that whenever we are talking of current, it is the flow of positive charges. Okay, now I will take one more example, and that is interesting in the sense that I'm going to talk to you about, because I've talked to you about Kirchhoff's laws, now I'm going to talk to you about what is known as the maximum power transfer condition, or maximum power transfer theorem, to wind up this lecture today. So let me tell you maximum power transfer theorem, because in many a text the power transfer from a network of series and parallel combination of cells, that's treated in a sense, and they get the result. Okay, so I'm not going into that, but I have a very simple circuit where this is the EMF, and this is the internal resistance, and this is the external resistance, in which we want the power to be maximum. Okay, and we change it. So we change it from 0 to infinite ohms, and then I will change from E over R in this case to 0 amperes. Okay. Now power has a formula I square R, where I is equal to E upon R plus R. Okay, you take this formula, but there is another formula, V square upon R. Initially, when we are increasing it from 0, then this R is greater than capital R. Therefore, the drop across it, okay, will be more as compared to the drop over here. And V square upon R, so the power consumed by this resistor, internal resistor, will be more as compared to that consumed by the external resistor. So as the value of R is increased, what we find is that the power keeps on increasing until then again the power drops to 0 as R is taken to infinity. I am just indicating things to you. So power R is equal to like this, so I can write this formula. Okay. power R is like that, and we obtain this formula. Now you see that for maximum and minimum, like here there is a maximum, so the dy or dx, that will become equal to 0. So the condition for the maximum and also for a minimum, that is equal to 0. I have told you in the beginning. Okay, so let me write ddr of dr, and I take e square out, so ddr of r into r plus r raised to the power of minus 2. Okay, from this form. Okay, now for two functions we have the formula that the first function into the differential of the second function plus the differential of the first function into the, I have emphasized it to you, and particularly in the case of vectors. So if like that, then I have e square as common, I'll write it r, and this will turn out to minus 2 r plus r raised to the power of minus 3 plus, of course, 1 into dr upon dr is equal to 1 into r plus r raised to the power of minus 2. There is no problem. So what I do is, I take this in the denominator, r plus r whole cube, and then in the numerator I get minus 2r plus, here I'll write r plus r, okay, so r plus r. Now this has to be equal to 0 in order to get a maximum power transfer according to the mathematics that we have. Okay. Now this can be equal to 0 if the denominator is equal to infinity or the numerator is equal to 0. So this is not going to be infinity. We are not going to talk of that situation, but we are going to talk of this situation. The numerator is equal to 0. So I get this as r minus r is equal to 0. So that means the condition that arrives, we obtain is the beautiful condition that the external and the internal resistances should be equal to each other, and this maximum power transfer theorem or rule or whatever you want to say will return it again when we are talking about impedances in the case of AC circuits. Okay, but for now this is only just to give you an exercise, okay, to show that it is this thing which determines as to what is the condition, because those people who solve the problem, they say that when the current is minimum, when the current is maximum, then the power will be maximum. No, that's not the condition. The power, ddr of power, that should be equal to 0. That is the condition. You may get it for a specific condition, the result, but actually this is the way that it should be done and understood properly. Thank you very much for the day.